You say something?
Yeah. He answered me. I said,
I'm bugging out. Okay, so we'll sort of get a slow start into this. If you look in the Indigo, I've got a number of things. It's mainly a reference material. There's a 2015 manual, 2020, that's the most recent. So you get the feeling that a lot of this is in progress. A Minuet reference, the plots, that's what it's supposed to look like at the end. But this is a talk given by Fragile that is quite useful and where I've stolen lots of the material. So you can take a look at that. And then for the folks using Docker, the instructions, we're developing them right now as we speak. And that's right there. So you can take a look at Crosstalk. I'm not going to go through it in detail, but what is useful, and he actually compiled a lot of the examples in this case. So the exercises are listed here, and they're all inside your VirtualBox. I apologize for the large size of the VirtualBox. We're going to do Docker up here. Do you want to work slide up there with them? Yeah, I apologize for the large size of the VirtualBox, but that way everything's in there and it works. Well, it did because I made one mistake, but we're going to fix that today. So just to get started, those of you with the image, hopefully you got it up and running, but let me just go through a couple of the things of the setup so you can see. And in terms of the general setup, if you turn on the shared clipboard, drag and drop bidirectional, it allows you to drag things in and out. The other stuff is default. For the system I have 16 gig. I'm using about half of that for my virtual machine, and I'm using 3 out of 8 threads. You decide what works for you. And for the display memory, I cranked it up a bit, to make it easier to display some things. Let's see, storage, of course, you'll pull up the disk image. Everything else is pretty similar. Depending on your VirtualBox, you may or may not support USB 3, so you can just dial that down to USB 2. And the shared folders, we can set that up later if you have questions, but that's a way for you to share materials between the VirtualBox and your host machine. So if you want to export what you've done, that's a useful way of doing it, but that's optional. And then down here in the description, some useful things. So the password, it auto logs in to VBox user. The password is xFit 2024. So if you have to do super user or something, and I also created a CNFS account with that password. It's always good to have two accounts. So if something messes one up, you can break into the system. So if everything goes well, should be able to start up and get that going. Is anyone having difficulty getting it to boot? And how are you guys doing on the Docker?
We need a USB with the example files on.
Did the one I give you?
I don't know who has it.
I think I got that back. Yeah, I think this is it. Yeah, and that only has exercise 1 and 3. We can look at it. All right, and if everything goes well, your machine should boot up and the screen is expandable. Okay. And so we're just going to start to start up. We're just going to get a terminal going. And as a sanity check, let me make this a little bigger so you can see it. Okay. I'll open this up so you can see the directory structure. Okay. And what we're concerned with mainly right now is the xFitter tutorials. And there they are, some documentation and 8 different tutorials that all work after you fix the glitch that I made when I was creating those. I created the image and copied it to 10 USBs and realized there was a glitch, but we'll go ahead. So I'll CD into the xFitter tutorial area. And then let's start with exercise number 1. Okay, and then if everything's working fine, you can just say xFitter and that will run. Okay, everybody good with that? And
Okay, you need this directory
okay,
to be the path to your downloads.
and this is pretty fast.
And then just type xFitter. So you don't want to be xFitter in there. CD to running. And then you're gonna need a space between. And then just simply type xFitter.
If you have a computer and you want to know, I can explain.
You don't run it, it's just like, it's like a. See how it says post dash IT, there needs to be a space between those.
And you can peruse the output later. But what's nice is there's a xFitter draw program. And so what you see is it created an output file. I had a previous output, it's moved that to output old. But if we want to see what the results are, we can use xFitter draw. Okay. And you tell it, just draw the results from the output file. And this will also won't take very long.
And now you need to actually you have a guide.
It's because of the return line.
You have a guide.
So now we can
There,
return
you just force the setup so that you.
just in return very fast.
And it's creating a bunch of plots in the output area. And if I use events to look at that,
Next one is to.
okay. So this is what you're looking at. Okay. And I just told it to plot some of the results. It will give you an example of what the PDFs look like in a couple of Q values. So
That's not xFitter flash.
So for example, here's X times the U bar, S quark, D bar, et cetera, at Q squared of 1.9, that's the initial value. And then it also shows you the results of the data minus theory. So for example, if I look up here, this is Hera run 1 and 2. It's the data from the Q squared 27 bin as a function of X. You see there are 3 data points. And what you have is the theory, including the shifts, are the dotted line, and then you have the data points with the error bands. And then down here, you've got the theory over data scaled, so you can see how well things fit. Okay, so that does that all for you automatically. And if you go to the if you go farther down, it will give you, there are many systematics, and it will give you the polls and the various systematics that it uses to fit. You can see those. And again, at the very end, let me modify this so I can see it on screen. On pages left. Okay. You can see here are the data sets that it fit. Here are the chi-squares per degree of freedom, the total, so we've got, pretty close to 1. Things are looking pretty good. And make this go away. And here are the parameters that was fit. And this is actually not a fit. I actually did not let the parameters be free. I just ran it and had it generate this. So, okay, so that's the absolute basic warm up. Any question on that? Everything seemed to be behaving? Yeah.
I have, everything works, but I get, each plot in the plot shows up twice. Is there a reason for that?
Well, let's see.
I could just ignore it.
Yeah, let me take a look at that later. And you specified a single output. If there's extra stuff in the output directory, maybe you can trash the output directory or try running it again, see if it persists. I've got this up a couple of details. If you look at the aliases, you see that I've actually aliases xFitter draw and xFitter draw no logo. So one of the reasons we put this in VirtualBox is it relies on root, and root is a monster. Getting all the dependency in root is absolutely a real nightmare. And in particular, one of the improvements of root broke this feature. So we'll fix it later, but stuff like that, that's why we're doing it in this way. Also, I said it was not a real fit. So if you look at if you look at some of the files here, let's say Emacs, the parameters file. Okay, and this is, of course, that's a YAML file, so it's in a standard YAML format. Make that a little bit bigger. You see that I've actually commented out, this is the part from Minui. Minui is what minimizes the fit, and I've actually commented out the migrad. So migrad is what actually varies the parameters and does the fit. I've done that because, this is pretty close to the minimum. It'll probably converge in a couple hundred iterations, but that's going to take longer than the hour we have to work in. So I've commented that out. But if you uncomment that out and let it run for a while, it will actually vary the parameters if you let it go. The Hess, this is the Hessian uncertainty. So what it will do is in parabolic space, it'll find the minimum, and assuming everything's parabolic, what it will do is it will walk up and down the parameters and figure out the error uncertainties. And it will do that in a Hessian method and dump it out for you. Again, I've commented that out so you can see what's going on. And again, in terms of the parameters, for example, here are the parameters that we're doing. Okay, we'll explain those later, but you see some of these are fixed, like the CGP is, it starts at 25 and has 0 step size. So that means that's going to be fixed. Again, some of these, this is the initial value, the step size. So you see some of these are fixed, some of these are variable, and that's the format. And then down a little bit more, we won't go into it, but the parameterization we're using is the HERA PDF parameterization. And you can specify things like, what you want for the evalence, devalence, but those are all detailed. So you can look into that and get a little bit more. The other one that's interesting to look at is the steering file. Okay, and okay. And so here, for example, this shows you what we're actually fitting. Okay, and so in the data files directory, things are organized very well. So we're going to do data. The data is going to HERA. It's the H1 Zeus combined, H1 and Zeus combined run, inclusive DIS. It's in this preprint 1506. And this is neutral current and charge current. So that's the data we're fitting. And of course, if you want to fit other data or you want to bring in your own data set, all you have to do is write a file that's in a YAML format, dump it in here and put it in here, and that'll do it for you. There's some other things you may like to look down and read through. You can kind of guess the formats of some of these things. There are clues. There's clues in the tutorials about how to do that. But that gives you sort of the basic idea. So, that's exercise 1. It's, kind of absolutely basic. We run xFitter, we run the draw. You, in principle, know how to open it up, vary parameters, and create the Hessian, things like that. So the next thing we're going to do is a different exercise with a little bit more detail. Are there any questions on this? Does everyone seem to get that okay so far?
I have questions.
Yeah.
Another USB.
Another USB? Yeah. Okay. And I think there's still one floating around out there that, no rush, but I would like to get them back again because we're doing the CTEC summer school in August and I'd like to use them for that one. So do you need an adapter?
Something's going.
No, I have that.
Okay.
Because
All right.
we don't have that public.
Okay.
So it's not.
Yeah, and again, the goal of this is you've got the VirtualBox, you can take it home. Installing this from scratch is a nightmare. So the idea is you've got a working version with all the paths, everything defined. So if you want to use it and install it natively, you can sort of look on this and copy and figure things out. If you get stuck, email us and we can try to help you. So the next exercise that we're going to do is exercise number 6. And that deals with the strange quark distribution. And Stefano was talking about some of the issues about the strange quark earlier. And this is rather interesting because traditionally when we did fixed target experiments, things like, see if I can scribble, You know, if you say, where do you get the strange quark information from? The answer is, it's kind of difficult. Because you've got, if I plot the PDF, you've got the, down distribution like this, and the strange distribution is quite a bit lower. And they both have the same charge, so if you try to decipher the strange underneath the down, how do you do it? They're the same charge, there's a lot less of them. And the trick is, what we do is we use neutrino deep inelastic scattering. And so we take a neutrino, it goes to an electron. If this is a minus, this is W plus. And then what I do is I take a strange quark, and this is negatively charged, and that goes to a charm quark, which is positively charged. Okay, so I scatter, this is a nucleon, typically iron or lead, something like that. And I'm probing this nucleon with a W, and when it hits a strange, it'll make a charm quark. Okay, and then the trick is, how do I tell that from, for example, I could do down to up, which is the dominant process. How do I tell the up from the charm? Well, the key here is the up is relatively massless, where the charm weighs about 1.5 JeV. And that extra mass means when it decays, it will decay occasionally semi-leptonically. If it decays to muon, it will kick off a muon at a very large, at a very large angle because of the extra mass. Whereas if this decays to muon, it'll be sort of contained in the jet. And so the difference is the extra mass of the charm. We're talking fairly low energy. The extra mass of the charm means you'll get an isolated muon. You'll get an isolated muon, and actually, typically, what they're doing here is they're doing mu neutrinos goes to mu. So this is mu minus. This will be a mu plus. And roughly speaking, what you do is you count the number of dimuon events versus the number of single muon events, and that gives you the down to the strange. And that's how we initially did it. And when we did that, what we found is kind of what we expected. The strange was about half of the U bar and D bar. And that's what you expect because the strange is heavier, U bar and D bar are easy to make, but strange you have to make with SS bar pairs. The strange weighs maybe half a JeV or something. It's a lot heavier, it should be suppressed. So we found this ratio here was about 1/2. That's what we guessed. And that worked just fine until about the 2012 data came in from LHC. And they analyzed that using the Atlas WC inclusive data, and they found something very surprising. They found out that this ratio was in fact something closer to 1.2, which is totally bizarre. You might imagine in a world where you're at very high energy, there would be symmetry between the S and the S bar, the S bar and the U and D, that this ratio might approach 1, but never in your wildest dreams would you imagine that would be greater than 1. And so that's what they found, and we're going to reproduce that. So that's what we're going to be looking at. And so we're going to move on to exercise 6, and we'll move into E6 area. Okay, and in here you've got 2 areas. You've got RS fixed and RS free, and that's RS is that ratio, the ratio between the strange and the U bar D bar. Okay, from fixed target we expect it to be 1/2. From Atlas WZ it gave you something over 1, and this is what we're going to run. So what we can do is I'm going to make 2 windows here. Control Shift N will make a second window, so I can do this in parallel. And I'll start with a fixed, RS fixed. Okay, if I go into the RS fixed area, so I've got the usual things, and let's take a look at the parameters. Okay. And what I'm doing here in this version, I've got the RS fixed to 1/2, and that's the value preferred by the fixed targets. So I'm going to fix that. I'm going to hold it there and then do a vary all these other things and see the best chi-squared and the best results I can get. Okay. Now, again, this is like the cooking show where they make up the batter, they shove it aside, and then they pull a perfect cake out of the oven. I've commented out the MyGrad here. I've commented out the MyGrad there. I think I've commented out the Hessian too. I've commented out those. If I haven't, let me make sure that's, so it's not actually going to be a fit. I did run this so it converged. And again, later when you have more time, you can open that up and make sure I really do have a minimum. But we're going to run this and generate the results. So inside this RxFix, I just say xFitter, and that will run. And while that's running, I'm going to switch windows and I'm going to go into RS free. Okay. And we'll take a look at those parameter values. Okay. And yeah, I've got everything fixed. And over here, okay, I had, it settled at 1.1. Here's my step size. Okay, so that's what I got when I ran it and let it be free. And I put in the Atlas WZ data, and that's the value it liked. Now, again, this is a fake because we're not actually going to let it fit because we want to finish before dinner. But it takes about half an hour depending on your CPU, so you can go ahead and verify that that's actually working. Well, I'm at it, let me open the steering file, and then you can see what we're fitting. Okay, so here's what we're fitting. We're fitting all the Hera data that we had before. And now what's new is we're fitting the Atlas, OAC Atlas W production data from preprint 1612, et cetera. We've got W plus or minus and Z, and that's what we're adding in. And that's what we're using to constrain Z, okay? So that's all set to go, and I'll run xFitter there. Okay, and that should go pretty quick, and I'll check my other window. And has that finished? Yes, that's finished. Okay. And what you see here is, what you see here, it's reading Apple grid files, and part of that's why we needed root, because the calculations are fairly sophisticated, and the integrals, the Stefano and the others showed you, are rather messy to do. But what we use is the grid technology to pre-compute all of that. We rearrange the order of the integrals, so we pre-compute all the integrals, and the last thing we have to do is the integral with the PDF. And so we use the Apple grids for that, and that allows us to do NLO or NNLO calculations very quickly without having to recompute those integrals. So that's what's going on there, and we really are doing higher order calculations very quickly with this grid technology. So that's almost done. Does it run for everyone? It's behaving for everyone? Okay, and that's finished. And now that made an output file. And now what I'm going to do is I'm going to go up one directory. So I apologize for the default colors here. I'm one directory up. I have RSFix and RSFree. And what I'm going to do is let me check one thing. Let me save that just so it doesn't get overwritten. Okay. And now what I'm going to do is I'm going to run xFitter draw. And what we did before is it ate the results of the output and showed it. But what we want to do is we want to compare those two results, where we had the strange fix at a half and where we let it be free. So I'll do xFitter draw. Okay, but now I want not just one file, I want both files. So I'll do RS fixed output, and I'll do RS free output. Okay, so I give it both output files, and it will actually do those together and compare them. So go ahead and try that. And that will take a little bit of time. It's saving the plots and plots at PDF. There we go. Okay. And let me go into plots. And let's look at, we'll take a look at the results. Okay. All right. And here again, it's plotted the results. Those are the U valence, D valence, etc. But what's interesting is on the next page where down here I have the strange. Here's the x times the strange at the initial scale. The fixed is the red curve and the blue is the free curve. And so as you expected, this was about a half the U bar D bar. This is 1.1 U bar D bar. It's quite dramatic. And again, I mean, there are lots of examples in here, but I picked this one because you can really see that, the difference and, things are working. And here it is. Here's the ratio. Here's the ratio of strange to U bar D bar. And sure enough, as a function of X, it averages to a half. So here it is looking something like that. And here it is up here, 1.1. Okay. So this Atlas data really is pulling the strange up in that direction. Now, a couple things. I haven't shown you here the uncertainties, but you notice on this log plot, there's some shape to the distributions, but when you get to small x, it really sort of flattens out and doesn't do anything interesting. So part of the reason for that is we're using a parameterization. We're using a parameterization for our distributions, and to good approximation, f of x equals x to the a 1 minus x to the b. And so this term sort of controls the high x stuff, but x to the a, that's about all you have to really control the small x. And it doesn't give you much shape independence. Now, with, when we're working the parameterization, that's one of the sort of difficulties that we're working with and trying to find a bit around. But you should ask Stefano this evening how the neural net handles that. And it turns out that actually gives a much more realistic uncertainty calculation down at small x because of the constrictions of the parameterization. But I'll leave that for the discussion. We keep going, and again, these are dramatically different as they should be. Let me move on. That's HERA data. Let me get to the, we want to get to the Atlas data. There it is. Here's some of the Atlas data. So here's Atlas, here's the Atlas data, for the MZ, data minus theory, and you can see the comparisons. You can also see quite a bit of difference here. It's hard to see here, but on the ratio plots, you can see the difference between the fixed and the free. And again, in the polls, again, some of them are pulling quite distinctly in the two cases. And let me just jump. Now here, you see it's a little bit off. It's formatted nicely. This is a little auto format. It's very nice for one column. It's a little hard to do in two columns. So what you can do, and let me see, so I cheated. Take them up. Yeah, so I this is all auto done. I cheated, and what I did was I dropped in a factor of 80% the text width. I shrunk it by 80% just so you could read it a little better. And so here's, if you do that. Yeah, there it is. So it actually, determine the right directory. So okay. Oh. Okay, I didn't drop it in. So we'll close this. Yeah. So here are the parameters, and you can see here, this is fixed at 0.5. This was again, it's not a fit because I turned off the Minuit parameters, but if you open it up, hopefully they converge and I didn't make any gross mistakes. And then if you go to here, again, you can see the chi-squared values. So, it's not a horrible fit. If I fix it at a half, it's up by about 150 out of 1,000, 10%. So it's a worse fit, but not horrible. And you kind of scan over and see, sort of looking for differences. In particular, you see right here, this Z rapidity. Z rapidity has a large increase in the chi-squared. That's one of the things driving that large strange. Okay. So again, I picked that one because that's a nice example. You can see the difference very clearly in the plots. Any questions on that? Is that behaving? How's the Docker one going? Okay, oh, great, okay, yeah. The Docker is much lighter weight, but it's, at least for me, it's a little bit more esoteric and complicated to do it. But if you guys, as you go, I put a Google Doc up there. Let me pull that up actually. And so this is sort of a joint effort, but it's sort of a joint effort, but basically as they're going through this, they're writing a manual so that other people can do this. We'll collect that in. Okay. All right. Questions on this point? And let me step back, give you sort of the big macro where what I'm looking for this. When you leave here, I want you to have a working virtual box with xFitter so you can do some of the basic things and you can go through all these tutorials. So if you get home and say, I want to do, just to show you the example, here's an example of, seeing how alpha S varies with this. If you want to drop in your data set and do a profiling and see how that will affect the PDFs, you can do that. Here's an example of small X-ray summation. You can plug in programs to do that. You can add your preferred PDF parameterization. That's something we've done with PhantomMass, where we've used the Bezier parameterization and to make it more flexible, sort of a la the neural net approach. Here, exercise 6 we've done. Exercise 7 is for a Pion PDF. So this can do, Hadron's Proton PDF. It can also do Pion's PDF. There is a version that will do nuclear PDFs that was used for the TUJ19 PDF. That is not being supported anymore. And if anybody is interested in project and is good at programming, we would love to have you take that and update it so it works with the new code. We've updated it to sort of all C++ at the top level, but in the process of doing that, it broke some of the things in the nuclear PDF. That would be particularly useful to EIC. So there are some projects, and see me later about that. And not only can it do Parton distributions, it can do fragmentation functions. Again, here's an example of the fragmentation function. Okay, so hopefully you have it, you go, and maybe a year from now or 6 months from now, you say, gee, it would be nice if I could do this. You've got the tools to do that and get started. Of course, if you get stuck, we'll help you with it. So what I'd like to do now is a couple things. Thanks to Marco, I realized that in the process, I upgraded the LHA PDF and broke some things. So we're going to see how to fix that. That might be useful. But the other thing you notice in the manuals, there's a 2015 manual, there's a 2020 manual. This is 2024. So there's nothing, within the last 4 years. What do? I'll show you, at least what I like is I like to use the debugger. And it's antique. I use DDD, which is built on top of GDB, but it's a nice way to, when you're trying to figure out what's going on, you can go in and actually look at the running code and inspect the variables, inspect things. So that's what I'm going to do next. And then just so you know what's coming afterwards, let me come back here and go into, let's see, let me go back into, let's go to RS fixed. Okay, in the output, okay, there's a bunch of stuff that comes out. For example, there's results.txt. There's where's the chi-squared? Yeah, anyway. But in here, there's this Proton directory. Okay, and in the Proton directory, there's Proton info and Proton dat. What these are the LHA PDF specifications of the PDFs. And so there's a convention LHA Lazuz LH Accord PDF. There's a specification. And if you dump your PDF in this format, many things can read that. In particular, what we're going to do on Monday, we're actually going to focus on LHA PDF using PDFs in the context of a Jupyter notebook, plotting them, integrating them, things like that. So again, you go out of here and you can plot them, you can integrate them to get basic cross sections and manipulate them. That's where we're going. In fact, that will be entirely outside of xFitter. So if you don't want to be working in the virtual box, if you have Jupyter installed and you have the LHA PDF Python wrappers installed, we can do that outside of xFitter. So that's what's coming next. Let me just show you the form of these. But this is what we're going to be using on Monday. So this is the info file. It's in a YAML format. So, you know, it's key colon data. So Xmax is this, Qmin is that, Qmax is this. Flavor is an array. -6 is the top anti-top quark. 1 is the down. It goes down, up, strange, charm, bottom, top. I have to be a little careful. Historically, we went up, down, strange, but that's funny because then it's plus, minus, minus, plus. This way it goes minus, plus, minus, plus, minus, plus. And 21 is, that's the convention, that's the Monte Carlo convention for gluon. Now, we also tend to like to use 0. And in fact, some of the things like main parts and OHA PDF, we use either 1, but that's why that looks a little funny. This is the info file that goes in, and then the what's actually dumped is, there it is. What's actually dumped is here. This is actually the data. So this is a PDF type. It's a central value. It's not an error value. It's in the LHA grid format 1. These values go from something small to, they go something small to 1. So these are the X values. Okay, it's gonna give you a grid in X, Q, and flavor. These are the X grid values. These are the Q values. These are the flavors, anti-top, the top, the gluon, and then it just lists them. And there are 13 values here. There should be 13 columns going across here, and it just prints them out. And there are lots of programs that read that automatically. So that's what we're going to be using on Monday. But let's go ahead and if you want to do some of the other examples, for example, if you try to run exercise 7, which is the Pion PDF, it probably will break because I updated the OHA PDF and that messed up some of the dependencies. So let's see how to fix that. And if you go to the main directory, inside the software directory is where everything is installed. And there's let me go to the, it's hard to see it on there. Let me go. So in the software directory, there's a bunch of dependencies, and these are all the dependencies that xFitter can use. Now, not every analysis uses all of these, and you don't have to install all of these depending on what you're doing. But the nice thing is in the VirtualBox, Fra went through and he installed all these. So anything you want to do will work in there. So that was very gracious of him. But the other thing I want to do is I want to go to the xFitter master. And this is where the master files are contained. Okay, and I made a mistake when I set up the boxes. So let's go in and fix that. Okay, and it turns out that I messed up some of the dependencies. So what we need to do is we want to we'll want to reconfigure and rebuild our executable. Oops. No. Yes. Here we go. Okay. So this is the make sh script. And so this is what you could use it for. You can use it to clean, uninstall, build, install, run, and reconfigure. Okay. And what we're going to do is we're going to reconfigure and reinstall it to fix the dependencies I broke. But we're going to do one more thing. So this is optional, but if you can go, actually, everybody go ahead, Emacs this file. It's in software, xFitter master. It's make.sh. This is the default command line for CMake, and it does release. But what we want to do is we want to comment that out, copy it down, and we want to do a debug build. Okay. So when you do the debug build, when you compile it, you can actually, when seeing debug mode, it will actually still optimize it, which is key if you want it to run fast. But what it does is include sort of the extra hooks that allow it to reach back, so you know the source code and things like that. That allows us to open it up with the debugger, step through it, but also have the source code available. So while we're going to the trouble of rebuilding it, if you would copy that over, comment out the release, and change that to a debug. Okay, is everybody with me so far? And do that carefully. As you saw, I messed up on my Emacs commands. Don't want to mess this part up. Everybody good there? Debug, capital D, lowercase ebug. All right, so I'll close that. And then what we'll do is I'll do make reconfigure, just REC is unique. And that will just reconfigure. It'll go back, look through the links. It'll tell me what it's finding, what it's using. It tells what the LA pack is, which version of QCD num, things like that. Okay. And the configuration is done. And now I go, same thing, install. And this will take a while. And you see mine goes fast because there's not much change. I had already done that. But you guys should be able to do that fairly quickly. Okay. Everything good so far? And I will leave that and go into, actually, let me make sure this works. All right. Anyone having trouble? Is it rebuilding okay? Everything working? Okay. So what I just did, I went on the right, where's my, so I was in the RS fixed, case, and I'm going to run that in the debugger. So I just said DDD xFitter ampersand, that runs in the background, so I get my command line back. And DDD stands for Data Display Debugger. It's antique, it's 10 years old, it's not being maintained anymore, but it's a very simple interface. It runs on top of GDB and allows you to look in and sort of see what's going on. So let me start that again from scratch, just so everybody's with me. So when I run that, it'll open up a window looking something like this. Okay, and if you don't have a command tool, you can say view command tool to make sure that pops up. I'm sorry about the small font here. There's not an easy way to change this. And basically what it does is, because I've linked it with, compiled it with the debug commands, it knows about the source code it comes from. And so here's the top level of the code. Okay, the main program is going to call xFitter. Now, I don't remember the details of what all the subroutines are. So what I'm going to do is I'm just going to run this, and I'm going to let it run for a while. And after it's running for a while, I'm going to interrupt it. Okay, and so when it gets into the core of everything, I'll interrupt it. And then what's nice is I can do a backtrace. Okay,
Like the line above.
and with the backtrace, what you see here is, actually, I should have had it run a little bit more.
And then control F.
Let's say continue.
Yeah.
No, it's still initializing. It's reading the Apple grid settle. That'll take a while. Okay. There we go. All right, now we have a more interesting, okay. So I just let it run a while, and kind of when it gets in the core of the program, I interrupt it. And then what I can do is I pull up a backtrace, and this gives me all the function calls, and I can read that off. And so let me show you kind of how that works. If I go up to the top, here's the call to main. main calls xFitter, which calls run xFitter, which calls et cetera, et cetera. You go all the way through. And as I click on things, it'll actually show me what the code is in the window. Okay, and I can see the whole structure of it. I don't have to go try to read the code. I don't have to read a manual. I can see the structure of it. And the key function is right here. This FCN, this is the function that Minuet uses to calculate the chi-squared. Okay, all the minimizer cares about is, I wiggle some parameters and you give me a chi-squared. And I wiggle the parameters and you give me a different chi-squared. And in this multidimensional parameter space, it makes a map of the chi-squared and minimizes it. And so that's where it starts. And you can see that it goes in here. In this case, I'm looking at reaction, deep and elastic scattering, neutral current. I'm looking at, there's some wrap files in here. I'm using MST, neutral current, next to next leading order. You can see the whole structure. And then I can go down here and I can examine variables. And if I right click on here, I can say print this, okay, or I can say display this. Okay, and it shows me the variables. And I can do breakpoints and stop points and all sorts of things. So that's where I say, sort of the manual, these things are evolving. It's always changing, especially when you're trying to find nasty little bugs. It's really difficult to do this. It's a crude program. This is a little better than GDB, but it gives you a nice way of doing it. And as long as you just link it with the debugging flags, you can go in there and do this and figure out what's going on. I mean, this is a very complicated program built up over years with many, many people. You'll never understand the whole thing, but with this tool, you can kind of go figure out which lines of code you have to focus on, what the values are, what's going on, and take a look there. So I, sort of from a practical point of view, I find that very useful. Any question on that? Anyone having trouble powering that up? All right. And then the last thing that I want to do, let me close. Oh, well, while I'm in here, just a few things. So you can display variables. You can also set breakpoints. I have none set right now, but for example, if I right click here and I set a breakpoint there, I've now set a breakpoint at the function reaction based DISNC. And then, every time it'll stop there. I can do watch points. I can make conditionals, things like that. But I mean, essentially the basics are enough to do that. The last thing I want to do is, let's go back up and let's go to exercise 7. Okay, that's the Pion PDF. And let's just check and make sure this runs. And if I say xFitter, okay, and now that is looking okay. All right, and that in your version, I had broken that in the original version. So until you do the reconfigure and reinstall to fix the paths, that will break. But at this point now, all 8 of those should work. And if you go into any of those 8 examples, you run xFitter, it will work. If you want to get fancy, you can pull it up in the debugger, take a look, and you're good to go. Okay, so I think at that point, that's most of it. You can play with it. If you want to take a break, go get some coffee. If you have questions, I'll take that. But at this point, you've got a working version with all the tools with the debugger. You're good to go. And then what we'll do on Monday, we'll take the output, the LHA PDF output. We're going to eat that with Jupyter using the LHA PDF library and manipulate that inside Jupyter notebooks. And you can see the PDFs, you can integrate them, and that allows you to do momentum fraction and cross sections and things like that. So that's all I have. How's the Docker stuff going? Is that
We got it fixed now. Seems to be working now.
okay? All right. And thank you for, again, you guys are writing the manual as you go, because whatever you write on there, we're doing the CTech school in August. I'm going to take that and copy it over. But that's the plan. So, all right, we will break there. Feel free to play as you want. If you have questions, I'll take them. But yeah, it should be good. But if you would recompile it, because until you recompile it, some of the exercises will break. But I hate to send you home with the defective version. So, okay.
No.
Let's not be funny.